Okay, so welcome everyone. I would like to request Professor Kamal to start his presentation. Professor Kamal, a senior member of IEEE from Gunma University, Japan. So his presentation is on intelligent transport system, smart car, future transportation with connected automated vehicles. So welcome everyone, and here you go, Professor Kamal, please. The floor is yours.
Okay, thank you very much. Can you hear me?
Yes, perfect voice.
Yeah. Okay. Thank you. Good night from Japan. It's 11 o'clock already. I think some participants are from various countries. So today I will introduce my research on the future road transportation with connected and automated vehicles. I have been working since 2008 in these topics, in this area, and today I will present my the development from very beginning until this point, the series of my research, two series of my research that I have conducted in various universities and also in together in collaboration with Nissan and Toyota. So this will include mainly my work, but all the idea about looking about the future of the road transportation systems. So I'm Kamal. Currently, I am in Gunma University in Japan. So move forward. So I would like to acknowledge at first for whatever I'm presenting, I must acknowledge these peoples who supported me throughout of my research, and still we are working together with some of them. And also since for about last 12 years, I was always supported somehow from the Japan JSPS research fund. So I must acknowledge those things. So before going into, let me introduce our research center, CRANTS, in Gunma University. So our target is to realize level 4 autonomous driving by this year. And we are we are largest, greatest, means the research center, public research center that have largest number of autonomous vehicles in the world. So we have 18 vehicles, including big truck, bus, and small cars for autonomous driving. And we are, you see here, we are also having some pilot project in different cities of Japan, where the autonomous bus are transporting public people from one place to another with just a service in real experiment service. So this is, I'm working here. I have joined in the Gunma University just 1.5 years ago, and I am collaborating with this center as well. Anyhow, let's move to the main topics on transportation. What are the problems in our existing road transportation system? You see the road transportation, I have a number, 65 slides, I think, so I pick up from here and there, but I will explain some part, I guess, those who are interested to work in this area, or maybe this will be suitable for them, and mainly some result, I will just fly to finish my work around 40-45 minutes. So anyhow, the road transportation is a complex system. Why complex system? There are various elements, independent elements, like each car is an element. Traffic signal is an element. So if we see the road network, various types of vehicles, the various types behavior among the vehicles, all make it very complex. We cannot model, we cannot predict it perfectly. So this is a very complex system, and you know, at this modern age of science, even we cannot prevent these kinds of problem, accident, emission, extra cost of fuel consumption. So you see in US only in 2017, 37,000 deaths. And if you see how many extra hour people spent, and you see some about 10% of the fuel consumption and other due to driving behaviors. Anyhow, if you see any data you can find, you know this fact. What is transportation and what I am going to present you, I think it's very easy for all the participants, regardless of their area, you understand what I am going to present. So now, why we cannot reduce this thing, accidents, emission, or congestion? The problem is the human driver. 100%, almost 100% vehicles are controlled by human driver, and they have limitation in sensing on also reacting, and not limitation, even some psychological factors. Some driver, they want to drive aggressively, so it's not about limitation. So I think this is the major reason that we are having this problem. How we can overcome this? The researchers have been working too much on this field always, but so far not much improvement. So let's see what intelligent transportation system, ITS, thinking, how, what they are going to introduce something new, that are, you see, the connected vehicle environments. The vehicles will communicate with each other so that they can share information with each other. So this is called connected vehicle environment. So autonomous driving vehicles. You see, this is one of the vehicles of my university. So if the vehicles are autonomous, then it can decide by its own, in own way, or intelligently, more intelligently, or then we can have some better transportation. So however, automated driving and connected vehicles, if you know the information of your surrounding vehicle, then how you utilize in an effective way so that whole transportation system work as a single body and shows the collective optimal behavior of the transportation. So if we can bring these three things, that means we are changing the current paradigm into, shifting the paradigm into new automated and connected paradigm. So all vehicle will be connected, so we can realize a congestion-free, utmost efficient transportation. But the thing is, even we have automated, connected, we need some innovation. We need research on this, what kinds of technology we can include and see how it can improve the traffic flow. So these will be the future of road transportation, connected vehicles and automated vehicles. At the same time, you see right now, if you see 0% are connected automated vehicles. So when we can have 100% connected automated vehicles, it need maybe 30, 40, 50 years, we don't know. So that means still the graduation will be very, shift will be very gradual, and we need some kinds of technology to support this transition. So anyhow, these are some of my work in the future. I just showing it in advance so that you can have some idea what kinds of work I have done so far. You see the if all the vehicles are connected and automated, we can realize intersection fully automated, no traffic signal. The vehicles will arrive at perfect time. They can turn left or right. There will be no collision, and they are just like moving at a highway, but on urban way. So we can realize this is possible. We examined, we proved this. What could be the maximum ceiling of advantage if we can realize this? How about the merging? These are the source of traffic congestion in many countries. Those have a lot of highways. The roundabout, some European countries, Malaysia, they have a lot of roundabout. How can optimize those things? So if we can bring this connectivity and automated vehicle technology, maybe we can realize these kinds of technology. Another direction, the cyber physical systems. The world is moving not only on transport in an integrated system, the society 5 smart city concept, how we can come up with some new idea. Right now, these will come in future, but unless we think, we come up with some proposal, some idea, some investigation, it will not be realized. So how we can integrate all these things to link with transportation, because without transportation, we cannot think a society, we cannot think a smart city or even industry. So that means that transport is the background, the things, how we can even IoT, we can use the individual information, we link with transport and find some new idea. So all these I am presenting to you so that you can, if you have a new idea, new thinking, you can think about, or you can ask me more about this. This is also from my expectation that you will ask some question, critical question to me. It will open my mind to have some new research as well. Okay, anyhow, let's move to my work. So in my research, although I am working as a application is transportation, my work is on, I use some specific algorithms, few algorithms. One of the algorithm is called Model Predictive Control, or MPC. What is MPC? I can, you can see here, I'm giving an example, the right side first. When you are driving a vehicles alone, you see your vehicles, you can see this yellow zone, you see there is an obstacle. So you think I will go in that way. So you make a plan, oh, this is your optimal plan. Then what happens? After moving little bit, you found another obstacle. So you change, after moving, sometimes you change your mind, you find another optimal way. Then again, another obstacle, you find another optimal way. So model predictive control is you optimize your plan, then repeat this optimization frequently and run. It's just like a playing chess, so that you are thinking you have several options. So which option you choose? So if I choose this option, the opponent will play in this way. So then I will choose another one. Then you choose what is the best and then repeat the process. So this is the key methods, model predictive control. And beside this, also I have been working in this area. In this, these are also in my area. My PhD in machine learning, reinforcement learning. So, but although I am working in this area, so I am open to work, use these algorithms to transportation system. Some of the other algorithms, you see some bio-inspired methods, how the robots or large number of entity can be, find their optimal way to get maximum benefit. How the swarm of robot can be deployed so that the individually they can spread around and find the various object. Maybe they're after tsunami or some natural disaster, they can find the object they need to support in this area, how we control a large number of things. So I am bringing this idea. These research are also have been published in some journal. So I am thinking how we can bring those kinds of idea in the transportation too. Anyhow, I took a long time in my introduction. So anyhow, traffic control in the future, anytime, we can see two types of control. One is network level, traffic signal, maybe traffic signal. You can see the vehicle control, individual car, how we accelerate, brake, what would be the speed, you turn or turn left, right, lane change, those kinds of things. So here one is motion control, another is route selection. So my work Today I will present two series of my work, traffic network control and vehicle motion control under these two topics: cooperative control of connected automated vehicles at intersection, and another one is efficient control of connected vehicles, individual vehicles, how we can control. So let me go to the signalized intersection. If there is a traffic intersection, you know the traffic light, it sometimes changes red and green. So green means you give the right of way for collision free smooth crossing of some vehicles, but red signal to others, but it causes inconvenience because those vehicles need to wait for long. And it causes, it reduce the capacity, it increase the inconvenience, fuel consumption, emission. So this is the problem in signalized intersection. Even we are talking about 100% automated vehicles, unless we change this traffic signal, they also have to wait like say in the same way. So it's very much inconvenient. So another inconvenient, there are some characteristics I think those who are new, they should understand here, the important point here. If all those vehicles are in a queue at a red signal, and you see when the signal changes from red to green, what happens? The first vehicle takes around 4 seconds to cross this intersection, because it takes extra time, because it has to start up from zero. Speed is zero, then speed up, then move. But after a while, all the vehicles can move at about within 2 seconds. So that means whenever there is a change in traffic signal, there is a loss of extra time. This is called as extra lost time. So any green signal, you see at the first part and last part, there is no traffic flow in the intersection. So at every change in traffic signal, there is about 4 second time loss. So that means effective green time is reduced. If you change the signal very frequently, your capacity, your effective green time will be low. That's why in many intersections, they choose the traffic cycle 2 minutes, 3 minutes, even as long as like this. And these are some graph, those who are interested to know. You can, depending on the cycle length, you can have this maximum green time, or it's also proportional. You just divide by 2, you will find the maximum capacity, how many vehicles can pass through the intersection. So if you make the signal cycle long, that means you need to wait at red signal for long in average. So this is the problem. You need a trade-off. Can we make the traffic signal cycle short? Then we can reduce the delay, but also it reduce the capacity. We don't want that. If we make it long, we can have higher capacity, but traffic delay will be high. How we can have some solution with connected automated vehicles? This is one idea. So I will just show 2 of my work. One is 100% connected automated vehicles I introduced at the beginning, how we can realize those things. Another one is 100% automated vehicles we can realize 50 years later. So how, meanwhile, what kinds of technology we can have? So I will introduce in case 2 in this research. So idea is, I'm going, the time will be factored, so I'm flying here. So idea is, we don't need a traffic signal. All vehicles can communicate with the intersection coordination unit, and we have a supercomputer to compute what would be the best trajectory for all vehicles, best timing, and pass back to the those vehicles using 5G technology or whatever future technology we have. So idea is, you see, very simple, very simple concept. Can we pass this car in this way? So then you don't have to wait at the intersection. So this is the idea. So here, what I come up with some optimization concept. How we can optimize all these vehicles at the same time, so we ensure there is no collision. So we just see if two vehicle crossing, this is the collision point, the center of their crossing point of their path. So if any one of these vehicles outside of this circle, that means this is a safe, no collision. But if both vehicles at same times arrive within the circle, that means collision. So we develop some kinds of function, risk function, that indicate the, depending on the position of two vehicles, that indicate whether there will be a collision or not. So anyhow, this is the main point. And also we want to run all these vehicles at some desired speed and acceleration, and considering the risk of sum of risks of all vehicles, we consider two vehicles from each lane. We compute their trajectory, then for maybe 10 seconds, 20 seconds, and we execute for 0.5 seconds and repeat this thing like model predictive control for their smooth crossing. So this is the result I have shown already. You see some vehicles is blinking, that means it will turn left or right. And you see from very far, they are coming in such a way that they don't have to wait at this intersection. So this work was published in 2014 in IEEE transaction. You can find in the reference I have given in this slide, or all this paper you can find in my Google Scholar. You can find the preprint version as well. So now see what are the advantages here, what kinds of advantages we have. In normal case, if we say 50% time is green, 50% time is red, both sides has equal traffic volume, then if we change the traffic volume per hour per lane, in the case we see the crossing time means 100 meters before the intersection, how much it takes time to cross this intersection. So in traditional traffic signal, traffic light, if you use, when the vehicles crosses 800, a maximum maybe 850 vehicles can cross. If we have more than that vehicles traffic volume, then what happens? The traffic, the vehicle has to wait 2 cycles, more than 1 cycle, some vehicle has to wait. So their crossing time increases and it goes maximum limit is like this. However, once we introduce our algorithm, our method, all are 100% vehicle in simulation, you see the crossing time is constant, like you are moving in the highway without any free flow. And you see their idling time is 0, no need to idle. And the fuel consumption, and see here the 800 something, we have almost double it is possible. And you see the traffic fuel consumption of these vehicles I have shown here. And these are the capacity, even we have a turning traffic 5%, even left and right turning traffic, you see that compared to traditional traffic capacity, it's near double situation. But the question is whether you feel comfort when your car is moving, crossing the intersection just after 2 or 3 meters, when the other side of car is moving. Even it's very smooth, maybe the human driver may not feel comfort. At the same time, if all vehicles are not connected, automated, we cannot realize those things. How about we think from now on some gradual implementation of efficient driving system, so that if it can support the automated car at a low volume, means low penetration. At the same time, if the penetration increases of connected automated vehicles, we can provide better support to them to have similar result. So we target the mixed automated and manual vehicles. What could be the intersection in the future, or in the transition period at least? So you see the traffic light, we usually divide the traffic in different group. We define like phase. So this show the traffic movements, phase 1, phase 2, phase 3. or if the turning traffic are not much, then we can operate the intersection like phase 1 and phase 2. So I come up in the idea that means the vehicles may not be automated 100% or not, can be semi-automated as well. We don't know when it can come up in the road in high volume, but we expect with 5G communication or other kinds of communication, all vehicles will be connected. In that case, can we think like we see the south and east by two link? I'm showing this example. Can you find the individual signal duration targeting for each vehicle so that their crossing time is minimum? If they are not automated, no problem. We are calculating the traffic line timing considering their individual arriving time. So we want to reduce their waiting time. You see some vehicles dotted line, they naturally arrive at intersection at this time, but this time is red, so that means he has to go cross this intersection at this time. So this is the delay time of each car. You see the difference between dotted line and solid line is the difference. Can we find a optimal pattern of these kinds of signal so that the total waiting time of all vehicles are minimum? At the same time, it will ensure the capacity of this intersection is higher than the number of traffic volume. This is the main idea of this work. And I'm not discussing details, so I represent the signal mathematically and formulate the problem, and we optimize, we estimate which vehicle can pass which time. If we change, you see, if we change the traffic signal a little bit, we can understand how much change will be their waiting time. So in that way, that to reduce the waiting time, we can find the optimal traffic signal. Of course, considering all four directions, not only one direction. If one direction, it's very easy, but four direction, it's difficult. So I just take some snapshot and make this animation that you see. We generate very short traffic signal considering the traffic volume. And when there is no turning traffic, there is no turning signal. So this is also explained here. So in this way, we can see 50% automated vehicles can improve the traffic flow as well. This is the way we develop the simulator, which simulate the things. So we gradually increase the traffic volume. When we increase this traffic volume, automatically you see the traffic signal timing is increased dynamically, and we can see this result, how our automated traffic signal system with connected vehicles work. You see the time passes and the traffic volume from four direction is increasing. You see the traffic signal volume, the duration also increases. So in this way, we proposed dynamically to change this traffic volume dynamically. Anyhow, you see traffic from two sides. These are the signals, how 50% of vehicles, automatic vehicles, when they receive the traffic signal one cycle ahead, they slightly adjust their arrival time so that they don't need to wait. If we can ensure shorter traffic time, we can ensure in that way. So now I see what are the existing best traffic signal control is called actuated traffic signal control. Still, I don't think even in Japan, we don't have everywhere, maybe very limited cases, because it's very expensive. You need to install the loop detector on the road and control the traffic in that way. But we compare with this system and we find for different penetration of automated vehicles, you see with the given result, you see the density around the traffic intersection, how it's in traditional cases it increases, but in our when 100% it's very low, and speed is almost higher than 30 kilometer per hour, while this traditional in cases it reduced below average speed below 15 kilometer per hour. And in the case of 50% AV, I think the same result. So this is the way we propose. This is also published research in transactions, so you can have this idea and find other result as well. Now I move on to my second topics. How we can control a connected automated vehicles in a better way so that they can improve the traffic flow, not create congestion or shock waves, and also improve the fuel consumption. So these are another, this is my original research. I started in 2008. The first one was eco driving. And in eco driving, I work with Nissan Automobile under the Japan government project. So what is the idea? This is my car and there is no connectivity. So I just can see this car, or I have the road map, digital road map of slopes. Then how can we, what would be the best level of accelerating or braking for next 20 seconds or 10 seconds so that the fuel consumption in long run is minimum, depending on this traffic in this information. So I optimize using model predictive control because I can take early action. If I predict what is going to happen in next 10 seconds or 20 seconds, I can easily make an efficient decision. So it will also strengthen the collision avoidance. Fuel consumption will reduce as well. This is my most cited paper published in IEEE transaction and intelligent transportation system as well. And I'm not explaining these things. I took Nissan Automobile. They give me experimental driving data. They collected only for me, and I developed some kinds of model. I use the Emson traffic simulator. We see the traffic, the fuel consumption can be improved around 15%. Now I want to see the another problem of eco driving using some YouTube video. I hope you can see it here. The shock wave, you see here some vehicle becomes slow and the shock wave is coming backward. I'm showing you again. So you see some vehicles are slow down in the this highway, but why some vehicles slow down? You see here, slow down, slow down. I'm not sure, slow down. This is the shock wave. This is called shock wave. The stop and go situation happen because of driving behavior of the human driver. So there are some experiment as well. So here you see in the circular path, the vehicles are asked to follow, maintain 30-meter gap and drive at constant speed. However, what happens? Some driver, because of human driver nature, some vehicles become congested, some are free flow. So this is called shock wave created, and this is the one of the reason of traffic congestion. So now we need to think beyond eco driving. So how we can have a better driving if we have the connectivity. You know the fundamental diagram of traffic flow. Those who are studying in civil engineering, they know in transportation system, when the traffic density, how many vehicles in 1 kilometer, very low, even the speed high, then the traffic volume is low. When the traffic density increases, traffic flow volume increases, number of vehicles per hour. However, there is some maximum point, this is called traffic critical density. After that, traffic congestion happens and speed drop. But even this is the maximum capacity, we cannot operate our road transportation at this level. Maybe only 85%, because in this is called meta-stable region where the traffic shock wave happens, as I showed. So now the idea is smart driving. This is my car. If I have information of all these 4 cars, all this car in my front, maybe 5 or 10 cars. And if we know this information of this car in advance, so we can take some early action. So let's see in the similar way what we can develop. This is the problem formulation. I am not going to explain these things. So here, this simulation in the circular path real experiment, I realized I developed this model and I run. You see, all these vehicles are running at constant speed, constant gap in the highway. This is the density and speed. You see, one vehicle is entering here. What happens at critical density? It creates traffic jam and it propagates backward. If it's propagate backward, that means it's create a congestion. So this is the traditional driving case. How about my smart driving? I propose here. This is my smart driving. I know the information of all these human driven vehicles. This is the dotted line shows. And same situation, the congestion start happening. You see the speed drops here. And what happens whenever smart driving, my vehicles see these vehicles reduce its speed. It also adjusts its speed and gap in such a way, you see that it reduces the gap and increase the speed so that the traffic jam cannot pass behind. So it alleviates the traffic congestion. So this is smart driving, called smart driving. This is the plot. If I plot this situation, relative trajectory, some vehicle enter and shockwave happens. And when a smart car, we introduce only one car at the early stage of shock waves, and then it can alleviate the shock waves. Anyhow, then that was a single lane road. How about multiple lane road? I work in Toyota R&D. I developed this, and this is also patented under the Toyota. So let me introduce this one. That here my host car, and these are the surrounding vehicles. If I know the information of all these vehicles, then I have another freedom to change the lane early to keep the flow smoother. So all this traffic model, and we see that we need the efficiency, we need the cost function, we want to ensure the safe merging, there is no collision, also no safe gap between same lane vehicles. So what I did, this is my car, and I decide using the optimization process whether should I continue running at the same lane, or should I change the lane? And what would be the perfect place to change the lane? So I calculate this thing for next 20 seconds, then every 0.1 second, 0.5 second, I repeat this optimization like model predictive control. And you see, this is one example. This is the case of autonomous or traditional car, TDS. These vehicles slow down. And what happens? It propagates backward later. And my automated car, you see, it can understand that whenever this car becomes slow, it can understand what is going to happen, and it speed up and change the lane. The traditional human vehicles still wait when its front car slow down, then it try to lane change. And with this simple comparison, you see, the average speed and fuel economy can be improved significantly. Now we introduce these kinds of vehicles in large scale in the traffic, in the merging road on the highway. You see, when 100% are traditional vehicles, these kinds of traffic jam happens. And now you see the pink car, and for the same situation of here, the pink car is controlled by the model predictive control, our developed methods. And you see, by this control effort, some of the vehicles adjust their speed wisely, looking the information the next 100, 200 meter, or make a lane change, and it can improve the traffic flow here. And significantly, you see in the case of 100% traditional vehicles, each vehicles, this is kilometer per hour, and this axis show kilometer per liter. Higher is the better for each vehicles, but however, you see some vehicles has to stop. But when we introduce 50% of this smart car, you see whole transportation, the most of these vehicles, even those are not automated, they improve their performance. If you see here, we observe the different percentage of the vehicles, autonomous vehicles in the traffic, and what are the improvement in average speed or average fuel economy. However, I already took 40 minutes, so I may take another few minutes to complete these topics. My current work is, you see the earlier work, we consider 100% information of 100% vehicles, means all vehicles, we know what their speed and position, then we can make the smart driving. But in the case when only a part of vehicles are connected, that means this is my host car, and this is the car V2 that communicates its information. This car communicates this information. So I know the speed, velocity, speed of this car here, here, and here along this road. But I don't know how many car in between, how many car in between. So how can we realize the same thing? So I come up with a new concept, completely new idea. It's called road speed profile. It's published in Transaction of Vehicular Technology. So you can have a look. So even we know the information of few vehicles, we estimate, we learn some way to find what would be the road speed profile. Even we don't know the information. If there were any car here, its speed would be like this. We estimate in this way. So I'm not explaining the way of mathematical derivation and other things. So this is my road speed road speed profile. So for evaluation, I took the NGSIM trajectory data provided by Federal Highway Administration of US. This open source data have been used for various studies in the world. So I took this data. These data were connected from the Hollywood, near the Hollywood. This is the highway, 5-lane highway. They collected the data for 45 minutes, all these vehicles. So anyhow, I show some data here. You see, I pick up some car along the road. This US data all is in feet and feet per second, the speed is. So you see, this is the x-axis data, and I plot some of the vehicle, all these vehicles data, speed data along this path, means x and speed here. So this marker shows the speed of individual vehicles. The green one, I use this mark. This is my host car that estimate the road speed profile. And the red one, we know the information only from this red car, red speed. The black, the speed of the vehicles, means black dot, are not known to these host vehicles. So it start estimating this road speed profile, this initial value. So what happens, you see, as long as these vehicles are moving forward, you see my car from these limited vehicles, from kind of vehicle to vehicle information, at least can understand there is a shock wave. Even the shape is not accurate, but no problem. If you have the volt speed drop, so you can make some decision that you have to take, adjust your speed or something. Even 50% or 25% V2V, vehicle to vehicle communication, we can see the host vehicle can predict the traffic flow speed profile in next 100, 200 meter in a better way to improve the driving behavior of these vehicles. Even there is some packet losses in data communication, even 50% losses. The speed in RMS error are not much significant. Still we can it works well, even better than the current case where we don't have information of car beyond the just immediate one. So anyhow, the smart vehicle that I proposed, instead of considering all information, all these vehicles, we just use the road speed profile and to predict my immediate preceding vehicles, and I have the similar result what I observed in the case of 100% automated vehicles. I am almost in the last stage, so this is the last topics, and this is under the review in IEEE transaction. I'm not going in much details. You see, if we have multi-lane road speed profile and smart driving, how can we smart driving? This is my given term that why we say smart. I am not thinking about only myself. I want to improve. In my behavior will help others to improve their driving performance. So you see, some part is congested and all this vehicle want to change the lane because the road is blocked or something happens. You know, when all these vehicles try to make a lane change at the same point, same places, so it's me crowd. You know, the crowd, even in a large crowd of people, some stampede happens, people die because when all want to enter somewhere, it creates congestion. So how can we create a situation, the traffic state, so that everyone can smoothly cross the lane, and can we use this road speed profile to provide those kinds of information? I am not showing those details of this here. So you see, this is a simulation result I use in traffic simulator here. So there will be congestion here. Many vehicles want to change the lane from this here to lane 1 to lane 2. And you see, when in the case when we don't introduce in certain traffic condition, if we don't introduce human driver, many vehicles has to wait long queue to enter the lane 1 in the highway. And lane 2, this is the speed profile, a different position, and this is the time, lane 1, lane 2, and ramp. And the color shows the speed. But when we introduce the smart vehicles, only 5% of the vehicles, you see, some vehicles here, when this vehicle is smart vehicles, they see some vehicles want to make lane change, this is congested, so it slow down early. So the main objective here to have the similar uniform fair speed means along the road over the lanes, means lane 1, lane 2 should have the similar traffic speed. If not, then the smart car will try to help to have the same speed that facilitate the other vehicles to smoothly change the lane and improve the traffic flow significantly if we see this result. So anyhow, these are the overall statistics. Only 5%, 2.5% vehicles can improve significantly as well. This is the way how connected vehicles, automated vehicles, maybe we can implement it in cloud computing way. So various ways are there to improve the traffic flow. So I must go to conclusion now. The connected vehicles, it bring the opportunities, but at the same time challenges. How we can deal with huge amount of data online in a fraction of second, and then process and show the best way to improve the traffic flow. So this is the challenge for our research community. We should come up with some new idea. Any idea, I think everyone knows about this, you can come up. Then we need to some innovative, we need to innovate the technology to have fully congestion-free, efficient, sustainable transportation system. You want to go from place A to B, you don't have to stop anywhere. Can we come up with these kinds of solution in the future, any smart society? Anyhow, that is my objective, and I introduce this will be the future of road transportation system. So we can come up, we can develop these kinds of things. So anyhow, at last, so what I want to say, I collaborate, I welcome any collaboration with any other university, faculty level, or also we are looking for motivated graduate student to work in this cutting edge research. So I am in mechanical engineering department. My background is electrical, but we accept a variety of students from various fields, no problem, various engineering field, even IT, they can join in our program because these research are multidisciplinary research. You can consider is a challenging something. These are some references. You can go to my Google profile. You can find all these all these files or preprint version of this paper. You can have a look, or you can contact with me if you are interested. Anyhow, I must stop now to have your question to discuss further. Thank you very much.
Oh, thank you, Professor Kamal. It's a really, really wonderful presentation and lots of ideas and results. So I would like to request and welcome the participants to raise your questions or comments. Please feel free. I mean, young researchers and students, don't feel shy. You are welcome to ask any question, or you can type. Anyway, so I have a few questions. So if you have questions, just raise your hand or type here. But my first question is that, I mean, uh, mm, you have shown that Gunma University, at your university, there are the highest number of smart cards. So how can I get one from you? That's a joke, by the way.
These are all are for research purpose, and some private company, they also sponsor something like some bus companies in the road. They are coming and they are converting their bus automated to test as well. So anyhow, still I don't have a car, autonomous car for me. These are for all experimental purposes. Yeah.
All right, so we have a question from Alif Al Maruf. His question is road speed profile work in access or collector road?
I'm sorry, can you repeat again?
Okay, is road speed profile work in access or collector road? I'm not sure. Collector road means toll road, I think.
Yeah,
Okay.
it's just give you what is the speed along the road in the network. Lane wise, so this is the idea I published in 2018. This this is my own new idea. So now I come up with these various kinds of road intersection. Then the things, if these kinds of information you can utilize for something, then we can come up. If we make a road speed profile, but we don't have idea how to utilize it, then it's meaningless. But it's possible along the road, anywhere, any types of road, even the toll road or merging point. If you see some vehicles intersection at red signal stop, you can show in the road speed profile as well that for certain times it changes. Also, as it's possible, what would be the prediction of road speed profile, so that can be used for improving your traffic flow. So any road is okay, any types of road are okay.
Okay, the next question is from Muhammad Minhajul Alam. Thank you very much, sir. How do you ensure safety in an uncertain situation for automated driving? Is there any guideline or rule?
Sure. Anyhow, in our work, we consider we have the information of my front car. This must be even human driver. And we ensure that in usual cases, even you brake at maximum braking, our algorithm ensure that there will be no collision. This is the most important point. But what happens if a vehicle's just a big stone drop from hill on the road and you suddenly stop? There is no way. So if human driver can stop, avoid the collision, if the sensor, the question is mainly the sensor. Why we cannot see the autonomous car on the road? Because the sensor is still not 100% accurate in detecting everything, everywhere, any weather, any even darkness or lighting condition. This is the only barrier. But in terms of algorithm, we already have the algorithm how to utilize this for efficient control or implement. So in terms of algorithm, it's safe. The thing is, if we don't have any information, but really something happening, that is not the part of my work. So anyhow,
Yeah.
many researchers are working on those fields.
Yes, thank you. Thank you. So the next question is from Jahangir Hussain. Salam sir, if ICU fails anyhow, it may occur an accident. How did you take the precaution for this if no have way to manually controlled emergency, or this thing is still in developed? I will be happy to know about this.
So I think you are talking about these kinds of
Sudden situation.
intersection. You see, all these vehicles, I am calculating every 0.5 second. Although I am planning for 20 second model predictive control, 20 second ahead we are, but whenever immediately, maybe I'm predicting some vehicles, I don't know whether it actually move in that way. If there are some changes in 0.5 second or fraction of second, I repeat this thing. Whenever there is some changes, I repeat the things and it can work well. But the thing is, if ICU fails, what happens? So individual vehicles has to slow down and take, they of course, they are taking the surrounding vehicles, they know each other. So your front vehicles has higher priority than you cannot hit them. So each vehicles in driving, if you are driving, you cannot hit your front car. So even the front car slow down, you must slow down. So these kinds of driving algorithm is there. But if ICU fails, what happens in the road in Japan as well? When big cyclone, the traffic signal is gone, no traffic light, it creates congestion. The same thing will happen.
Okay, someone raised the hand, but if you have questions, so please raise the hand again or unmute and ask questions. So I have a question like, how much scopes of reinforcement learning in your work? Because you mentioned that you worked on that before. So this is number one. And number two is that any available data that young researchers can explore based on this. So can you give some point?
Okay, I know the community of ICEV and IVPR, most are from pattern recognition and image processing field. So if you talk about data, so some people are working on the data, but you know that data means existing traffic data. Mm-hmm. So existing traffic data you can use for finding the traffic congestion or finding the route in current condition. These kinds of things you can have the data. There are some kinds of data, but my research is not, I don't want data of current system. Maybe for just prediction or something, we need to come up with new technology that can improve the traffic flow. That's why it's not a better we don't have those kinds of data to work, but you can start working how a vehicles follow other vehicles, a simple model. You can run, you can understand how human driver drives a car using simulation. Then you introduce car, there are some open source program. Even I have some simple developed simulator to apply in to using MATLAB. So you can start working with these things and come up with your algorithm. Now the reinforcement algorithm. Reinforcement algorithm is, of course, it's a it can learn what is the best from the failure and success or whatever the feedback. But it's a long process of learning. There are a lot of research recently that learn the traffic signal timing or lane changing decision, whether also there could be some other option too, I'm sure. So these are some ways to for reinforcement learning. The reinforcement learning, the original problem is if you have huge data, then your decision, how you state and action space, what Bellman told, the curse of dimensionality, you must have experience of all this state, so that after that only you can show your optimal behavior. So this is the big challenging. However, the neural network, I did use a neural network long ago. Now deep reinforcement learning, of course, I think big opportunity to work in this area. Those who have interest, I think they can come up in this area to see.
Okay, thank you. There is another question, Nazirul Hassan. How do you model the spatial interaction between cars using RSP in your latest work? He meant like multi-lane RSP. By the way,
Okay.
Dr. Kamal, you can see the questions on the chat box, so that, I mean, yeah. So how do you model the spatial interactions between cards using RSP in your latest?
Okay, there are many human card following behavior model, like Gibbs model, intelligent driver model. If you just search intelligent driver model IDM, this is the most popular recently. You can find this formula in Wikipedia, you can find this paper. So those intelligent driver, unfortunately, I did not introduce here. So if you, this is a simple equation. What is the speed of your front car? What is your speed? And what is the gap? Using this information, it says what would be the acceleration, how human driver decide this acceleration. Because I'm talking about human driver, we are considering still now RSP, all vehicles are human driver. So we use simplest, means traditional human car following behavior. There are a lot of behavior you can find. Gibbs model, IDM is the most popular, I told, but you can find others as well.
Okay, thank you. Mr. Shamim has a question. He thanked you. So can you tell us about the best known method for predicting future velocity or acceleration of preceding vehicles?
Okay, this is the most challenging thing, and you know, the model predictive control I'm working, the most important thing, you must predict your vehicles, how it works well, how it moves. So in eco driving, I consider what is it, current speed and current velocity. I just consider it will continue few seconds at the same pattern. This is one way. Some researchers, until my work, or researchers just consider they will move at a constant speed or something. Then still I found some that when preceding vehicles is running steadily, maybe 50 km/h, but 200 meter, there is a red signal. Still it's running steadily. I know it will stop in the red signal, but what would be the pattern? So then I develop some model using real driving data. This is the one, another way. Again, I want to predict my preceding vehicles. Here, if we know the information of all this car, then using car following model, I find the interaction between these car, these car. By iterating them, I can find what would be the behavior of immediate preceding car. It gives better result, of course, because I know these vehicles, when they are running at a constant speed, steady speed, you know, even in we can predict in that way. When some vehicles are moving, it will move few seconds at the same way. We just consider if it's rainy every day, maybe next day will be also rainy. So this is called persistent prediction. There are some concepts used in weather forecasting. So my professor asked me to, you can utilize this idea to introduce. So from the front car, I don't know what it's the car of its front. So then I use this persistent prediction. So if we can, that's why we need the connectivity to predict our vehicles in a better way. I'm not sure whether you are happy with this answer.
Thank you. Thank you. I hope that Shamim is happy. If not, then he can ask another question. No problem. So feel free to discuss and share your opinion. So next question is from Kaniz Isha. Sir, can we use traditional velocity or acceleration formulas for real life traffic scenes without inducing much higher errors?
So what do you mean real life traffic acceleration formula, real life? Of course, you know the velocity, if you apply acceleration, how velocity changes. This is a simple formula. And how the acceleration velocity changes the position we learn at intermediate level. So we have to use this formula. This is basic formula, no way. But the thing is, how you find what would be the acceleration of this vehicle? It depends on its surrounding condition. So that part you have to find some way. Another way can be you can find a learning method, or you can, from physical data, you can find training model to find how your car, how the car you are going to predict, how it decide the acceleration. If you know the acceleration, you can find other things. So I think all these car following model, different researchers proposed, they calibrated with the real data to see how the vehicle decide the acceleration. At least you need those formula to use your real traditional velocity acceleration formula.
Thank you. Thank you. So just one last question. This is from me. Like you mentioned that AIM SUN AIMSUN microscopic traffic simulator in one of the last slides. Is it key to get, I mean, how to get the access of those simulators?
It's a very expensive software and not available to work. Okay. But I know I want to tell there are some software like a simulation of urban mobility. You can see simulation of urban mobility, SUMO. You can search for that. You can find this is the means freely available. You can work with this. You can have a Python link to collect the data. You can link with other software from this simulator. The AIMSUN, it's about more than $10,000 for the simpler version I have been using. So this is the second most popular and means most functional simulator. So anyhow, it should not be a barrier for anyone want to work. There are free software. Maybe you need to code a bit more, not friendly, but it should be sufficient for you, the beginners.
Thank you, Professor Kamal. I mean, we are happy to have a good number of participants and several teachers from different universities like Dr. Sheikh Sadi, Dr. Janna, Umar Sharif from Kuwait, Mullah Rashid from Asia Pacific, University of Asia Pacific. And you'll be delighted to know that Professor MMA Hashim from Kuwait, he is also present. And Professor MD Abdul Razzaq, he's the Pro Vice Chancellor of Green University of Bangladesh and a Professor of Computer Science and Engineering Department of University of Dhaka. So I mean, we thank you all for your participations, and the next, after 2 weeks, we'll have the next presentation by Professor Andrew Nialt. He's a wonderful speaker, so feel free to join, and we welcome you to consider the following conferences, upcoming conferences in 2021 to participate. So at the closing, I would like to request Professor MD Abdul Razzaq to give a closing remark, please. Professor Razzaq.
Thank you very much, Professor Atikur Rahman Ahad, for organizing such a very important and timely discussion topic. I get a bit late to join, 10-15 minutes, but I was listening very carefully the topics that was shared by our respected Professor Abdul Samad Kamal. I believe this discussion, question answering session helped a lot, and it was a very memorable event in today's evening. Well, the questions that were coming up my mind were answered gradually, many of them in these discussions. For example, the related research need very reliable communication among the vehicles in successive locations. And someone asked one question related to this. There are very recent technologies, vehicular ad hoc networks, cognitive radio communication technologies related to vehicular communication. Also, there are roadside units in many roads that are also helping out to better communicate among the different autonomous vehicles running on the road. So in that side, given that Professor Abdul Samad Kamal considered that there is reliable communication system in the underlying, and based on that, his models are working. That's very nice. He also looked into the problems related to lane changing, wherever multi-path roads, multi-lane roads are available with different speeds. That is also interesting. He also considered some vehicles coming into the road from some side roads that also slow down the different vehicles. That was also interesting. Eco driving, the concept of eco driving was fantastic, I believe, and all these discussions really helped this session to be a rich one. Well, I put only one concern related to timely computation of the optimal function or the optimization framework that are being considered over there to find out a particular route. As we are observing that many vehicles, I mean traffic loads are increasing, the different conditions, diverse conditions are also increasing, and definitely it will make the computation time longer. So this is a challenging issue, definitely. Even though our autonomous vehicles had higher computation capacity devices, but still I believe it would be a challenging one to solve a particular optimization problem within the limited time, be it a linear, non-linear, multi-objective, or convex, or different types of optimization problems we will solve. So I would like to have some comments regarding solving the optimization problems within the expected real time to take decisions at the real-time scenario. So thank you again, Professor Kamal. I believe I love to communicate with you. regarding some future collaboration related to seminars or conferences like this, or some exchange relationship. I am also working somewhat related, but maybe the exact problem is different, but also working in somewhat in related areas. So thank you again, Professor Kamal, and thank you again all the participants who are attended here. I always emphasize communication in between the NRBs and the young researchers. And our Professor Atikur Rahman Ahad is relentlessly working to increase the networking amongst the researchers working in different corners of the world. I really appreciate Professor Atikahar for organizing this one. Thank you very much. Thank you.
Thank you
Thank
very
you very
much.
much.
And we hope to see you all again after 2 weeks. Professor Anton Nyold is a wonderful person and very big researcher, very well known in the community. He has a good number of books and a legendary person. So, and he attended ICIEV-IVPR conference in Bangladesh, Japan a number of times. You know him, and we hope that his presentation will be delightful. And then after 2 weeks, 27th November, we'll have Professor Nikola Banovic from University of Michigan, Ann Arbor, on human-computer interactions. He's another very exciting person. So I hope that you will enjoy two of my friends' talk in the coming weeks. And please inform others so that more can get the benefits from this. With that, I thank you all, especially Professor Kamal, for his time and exciting presentation. Stay safe, stay well, and do the best. Let's try to do more research and do the best. Thank you so much.